Good day, esteemed researchers and curious minds tuning in from around the globe. We're thrilled to present ChatHuman language-driven 3D human understanding with retrieval-augmented tool reasoning, a groundbreaking study by Jing Lin, Yao Feng, Weiyang Liu, and Michael J. Black. This research tackles the complex challenge of teaching language learning models to accurately utilize tools, especially in the realm of 3D human understanding. Stay tuned as we delve into our innovative approach and the intriguing insights it has yielded. In this slide, we delve into the key motivation behind our research. We recognize the significant challenge of teaching language learning models, or LLMs, to accurately discern when and how to utilize tools. This is not a straightforward task. The difficulty lies in the fact that we need to summarize all potential application scenarios and requisite background knowledge within a prompt. This becomes particularly challenging when we consider the vast number of professional tools related to 3D human tasks. Each tool has its own unique usage scenarios and requires specific background knowledge for proper utilization. As the number of tools grows, the complexity of their descriptions within the prompt also increases. This complexity makes it harder for the LLM to use different tools, especially new ones for which it was not trained. This is the problem we aim to solve. And in the following slides, we will discuss our proposed solution. Moving on to our key highlights, we identified a significant problem in the field of tool usage by language learning models, or LLMs. As the number of tools increases, their descriptions within the prompt become longer and more intricate. This complexity poses a challenge for the LLMs, especially when they encounter new tools that they haven't been trained on. It's like giving someone a toolbox without a manual. They may struggle to use the tools effectively. This issue is particularly prevalent with specialized tools related to 3D human tasks. So, how do we address this? Stay tuned as we delve into our proposed solution in the next slide. Moving on to our key highlights, we've discovered some crucial insights that have significantly impacted our work. Firstly, we found that scholarly articles are a goldmine of information that can be used to construct high-quality instruction following data and tool documents. This approach allows us to cover a wide range of application scenarios and provides a comprehensive understanding of each tool's functionality. Secondly, we've leveraged the power of language model-based agents, or LLMs, to utilize their world knowledge to discriminate and improve tool performance. This means that our system can effectively discern when and how to use different tools, even those it was not initially trained on. This has opened up new possibilities for us, enabling the system to handle a broader range of tasks and scenarios. These insights have been instrumental in our progress and have paved the way for the development of more efficient and versatile systems. Stay tuned as we delve deeper into these findings in the following slides. In this slide, we delve into the key contributions of our research. We've introduced a novel mechanism known as the paper-based Retrieval-Augmented Generation, or RAG, to enhance tool usage. This mechanism leverages the wealth of information found in academic papers related to each tool. We feed these papers into GPT-4, prompting it to rephrase the tool functions and generate potential user queries for tool activation. This approach allows us to cover a wide range of application scenarios and provides a comprehensive understanding of each tool. This is a significant stride in our quest to improve tool usage accuracy and versatility. Moving on to the key highlights of our method, let's delve into the retrieval process. This process is a crucial part of our approach. It works by matching the text embedding of a user's query with those within our tool documents. This matching is done using a pre-trained text embedding model. Now, you might be wondering, what happens after a match is found? Well, the retrieved sample is then merged with the user's query. This combined information is provided to our agent as an in-context-learning example. This way, our system is continuously learning and adapting to better serve the user's needs. This process is not only efficient, but also highly effective in dealing with complex tool usage scenarios. Moving on to our key highlights, we've made some significant discoveries. Firstly, we found that incorporating the content of academic papers into our model consistently enhances the accuracy of tool usage. This is a major step forward in our research. Secondly, we discovered that the abstract and introduction sections of these papers are particularly effective. They often contain the most crucial information about the tool's function and potential applications, which greatly aids in improving performance. Thirdly, we found that the choice of text embedding model doesn't significantly impact the performance of our method. This is a testament to the robustness of our approach. ChatHuman, Lastly, in a multi-turn dialogue setting, ChatHuman outperforms other models. It effectively understands the comprehensive context within the dialogue and uses the tool correctly to solve problems. This demonstrates its superior capacity in real-world scenarios. These key results highlight the effectiveness and robustness of our approach, and we're excited about the potential applications. Stay tuned as we delve deeper into these findings in the following slides. Let's delve into the challenges we face when teaching language learning models, or LLMs, to effectively utilize tools. The first hurdle is the difficulty in summarizing all potential application scenarios and requisite background knowledge within a prompt. This becomes even more complex as the number of tools grows. Now, imagine this complexity amplified when dealing with specialized tools, particularly those related to 3D human tasks. Take a look at the figure on the screen. It illustrates our proposed solution, a paper-based retrieval-augmented tool usage. Here, we feed the academic papers of each tool to GPT-4 to build a comprehensive document for each tool. During inference, a relevant sample is retrieved from these documents and provided to the LLM-based agent as an in-context example. This approach significantly improves the tool usage accuracy. In the following slides, we will delve deeper into how this mechanism works and the results we've achieved. Stay tuned. Let's delve into the limitations of existing approaches. Current methods typically involve summarizing the usage scenarios and input arguments of each tool within the input prompt of the language learning model, or LLM. However, these methods often fall short when it comes to specialized tools. Now, if you look at the figure on the screen, it illustrates our proposed solution, the paper-based retrieval-augmented tool usage. Here, we feed the academic papers of each tool to GPT-4 to build a document for each tool. During inference, a relevant sample is retrieved from these documents and provided to the LLM-based agent. This serves as an in-context example, significantly improving the tool usage accuracy. This approach addresses the limitations of existing methods, particularly for specialized tools, and paves the way for more accurate and efficient tool usage. Stay tuned as we delve deeper into this innovative approach. Now, let's delve into the heart of our approach, the paper-based retrieval-augmented generation, or RAG mechanism. This innovative method is designed to enhance the usage of tools, particularly in complex scenarios. Here's how it works. We feed academic papers related to each tool into GPT-4, our language model. GPT-4 then rearticulates the functions of these tools and generates potential user queries for activating them. This process is illustrated in the figure you see on the screen. By leveraging the rich information in academic papers, we can create a comprehensive document for each tool, which serves as a valuable resource during inference. This approach not only improves the accuracy of tool usage, but also makes it easier for the model to handle new tools. So, in essence, we're using the power of AI to make our tools smarter and more user-friendly. Let's delve into the implementation of our retrieval process. This process is a key component of our paper-based retrieval-augmented tool usage. As you can see in the figure, academic papers related to each tool are fed into GPT-4. This creates a comprehensive document for each tool, which serves as a knowledge base during inference. Now, when a user query comes in, we retrieve a relevant sample from these documents. How do we do this? We use a pre-trained text embedding model to match the text embedding of the query with those within the tool documents. This allows us to find the most relevant example to the user's query. Once we have this example, we merge it with the user query. This combined information is then provided to our agent as an in-context learning example. This process significantly improves the accuracy of tool usage, making our system more effective and user-friendly. In essence, our retrieval process is a powerful mechanism that leverages academic knowledge to enhance tool usage, making it more accurate and efficient. On this slide, we delve into the effectiveness of our paper-based retrieval-augmented tool usage, or RAG mechanism. This mechanism is designed to improve tool usage accuracy by leveraging academic papers related to each tool. These papers are fed into GPT-4, which then builds a comprehensive document for each tool. During inference, a relevant sample is retrieved from these documents and provided to the LLM-based agent as an in-context example. This process is illustrated in the figure you see here. Now, let's talk about the effectiveness of this mechanism. Our studies have shown that it's particularly effective in zero-shot settings. But that's not all. The LLM-based agent can also utilize its world knowledge to discriminate and improve the tool performance. This means that the agent can not only use the tools effectively, but also enhance their performance by applying its general understanding of the world. This dual functionality makes our RAG mechanism a powerful tool in the realm of language model learning. Let's delve into the role of scholarly articles in our approach. These academic papers serve as a rich source of information, helping us construct high-quality instruction following data and tool documents. They provide detailed usage instructions and diverse application scenarios, which are crucial for our method. As illustrated in the figure, we feed the academic papers of each tool to GPT-4 to build a document for each tool. During inference, a relevant sample is retrieved from these documents and provided to the LLM-based agent as an in-context example. This significantly improves the tool usage accuracy. So, in essence, we're leveraging the wealth of knowledge in academic papers to enhance the performance of our tool. On this slide, we delve into the evaluation and metrics used in our study. We conducted an ablation study to dissect the effects of each component of the academic paper in guiding tool usage. This allowed us to understand how different sections of the paper, such as the abstract or introduction, influence the accuracy of tool usage. We also evaluated the tool use accuracy within multi-turn conversations. This is crucial in real-world scenarios where models need to correctly use the tool based on the context within a dialogue. In terms of metrics, we use the success rate for seen and unseen tools, the successful rate of arguments, and the F1 score for human-object interaction contact detection. The figure you see here illustrates our paper-based retrieval-augmented tool usage. The academic papers of each tool are fed to GPT-4 to build a document for each tool. During inference, a relevant sample is retrieved from the documents and provided to the LLM-based agent as an in-context example to improve the tool usage accuracy. This approach has shown promising results in improving the accuracy and robustness of tool usage, especially in complex multi-turn dialogues. Begin a frame title are related works. Begin itemize. Item slide 1. Introduction to related works. Begin itemize. Item. As we delve into the world of language learning models, or LLMs, we find a variety of approaches to teaching these models to utilize tools. Each approach has its unique strengths and challenges, but a common thread is the need to understand tool usage scenarios and input arguments. Item. The complexity increases when we consider specialized tools, especially those related to 3D human tasks. These tools often have multiple usage scenarios and require a certain level of background knowledge for proper utilization. Item. The challenge lies not only in summarizing these scenarios and arguments, but also in managing the growing number of tools and their increasingly complex descriptions. Item. To address these issues, we introduce a novel approach, a paper-based retrieval-augmented generation mechanism. This mechanism leverages academic papers to re-articulate tool functions and generate user queries, thereby facilitating tool usage. End itemize, end a frame. Begin a frame title are related works. Begin itemize. Item slide 2. Existing approach, summarizing tool usage. Begin itemize. Item. We've seen how the traditional approach involves summarizing the usage scenarios and input arguments of each tool within the input prompt of the language learning model, LLM. This method, while straightforward, often falls short when dealing with specialized tools, particularly those related to 3D human tasks. Item. These tools often have various usage scenarios and require a certain level of background knowledge for proper utilization. Summarizing all potential application scenarios and requisite background knowledge in a few sentences within the prompt can be challenging. As the number of tools grows, the descriptions of these tools in the prompt get longer and more complex, making it harder for the LLM to use different tools, especially new ones for which it was not trained. End itemize, end a frame. Moving on to our third slide, we delve into the limitations of existing approaches. We found that the traditional summarizing approach often falls short, especially when dealing with specialized tools. The challenge lies in encapsulating all potential application scenarios and the necessary background knowledge within a single prompt. This becomes increasingly difficult as the number of tools grows. The complexity of the descriptions escalates, making it harder for the language model to use different tools, particularly those new ones for which it was not initially trained. This issue is particularly prominent in the realm of 3D human tasks, where a multitude of professional tools are in play. So, how do we address these limitations? Stay tuned as we explore our proposed solution in the upcoming slides. Begin at frame title are related works, begin itemize, item slide 4. Existing approach, tool definitions, begin itemize, item. Let's delve into an existing approach where tool usage is formulated as ytool equals f5 xq xt, with xt representing tool definitions. This method, while straightforward, often falls short when it comes to specialized tools. Item. Particularly in the realm of 3D human tasks, where a plethora of professional tools exist, this approach struggles. The complexity arises from the diverse usage scenarios and the background knowledge required for each tool. For instance, the HMR tool poses questions like, can you estimate the pose of this person? Or, what are the SMPL parameters? Item. The challenge lies in summarizing all potential application scenarios and requisite background knowledge within the prompt. As the number of tools increases, the descriptions become longer and more complex, making it harder for the LLM to use different tools, especially new ones for which it was not trained. End itemize, end frame. Moving on to slide 5, we delve into the need for a new approach. Traditional methods often struggle with specialized tools, especially when there are numerous professional tools related to 3D human tasks. These tools have various usage scenarios and require background knowledge for proper utilization, making it challenging to summarize all potential application scenarios and requisite knowledge concisely. As the number of tools grows, the descriptions get longer and more complex, making it harder for the language learning model to use different tools, especially new ones for which it was not trained. To overcome these limitations, we introduce a paper-based Retrieval-Augmented Generation, or RAG, mechanism to facilitate tool usage. This mechanism leverages academic papers associated with each tool, prompting the model to rearticulate tool functions and enumerate potential user queries for tool activation. This approach allows us to cover a wide range of application scenarios and compile a document consisting of question-answering pairs about tool operation for each tool. These documents serve as an auxiliary knowledge base during inference, enhancing the model's ability to use different tools effectively. Stay tuned as we delve deeper into this mechanism in the next slides. In this slide, we delve into the technical details of our proposed research. We introduce a novel mechanism known as the paper-based Retrieval-Augmented Generation, or RAG for short. This mechanism is designed to enhance the functionality of language learning models, or LLMs, by facilitating their usage of tools. As you can see in the figure, the RAG mechanism works by inputting academic papers related to each tool into a model like GPT-4. This model then rearticulates the tool functions and generates potential user queries for tool activation. This approach leverages the extensive background, detailed instructions, and varied applications found in academic papers, allowing for a wide range of application scenarios. This innovative mechanism is a significant step forward in our quest to improve the accuracy and efficiency of tool usage in LLMs. In this slide, we delve into the crux of our research: the challenge of teaching language learning models, or LLMs, to accurately discern when and how to utilize tools. This task becomes increasingly complex with the rise in the number of professional tools related to 3D human tasks. As you can see in the figure, we've illustrated our proposed solution: a paper-based retrieval-augmented tool usage mechanism. This mechanism leverages academic papers associated with each tool, prompting the model to rearticulate tool functions and generate potential user queries for tool activation. The goal here is to overcome the limitations of traditional methods, which often struggle to encapsulate the diverse usage scenarios and requisite background knowledge of specialized tools within a concise prompt. Our approach aims to simplify this process, making it easier for LLMs to use different tools, especially new ones for which they were not initially trained. On this slide, we delve into our unique approach to the problem at hand. We leverage the wealth of knowledge contained in academic papers associated with each tool. These papers are fed into GPT-4, a powerful language model. GPT-4 is then prompted to rearticulate the functions of these tools and generate potential user queries for tool activation. This innovative method allows us to cover a wide range of application scenarios and effectively instruct tool usage. The figure you see here illustrates our paper-based retrieval-augmented tool usage. This approach not only enhances the accuracy of tool usage, but also broadens the scope of potential applications. On this slide, we delve into the unique aspects of our approach. Central to our method is the retrieval process, which is implemented by matching the text embedding of the user's query and those within the tool documents. This is where our approach stands out. We use a pre-trained text embedding model to facilitate this process. This model helps us to accurately match the user's needs with the most relevant tool, ensuring a more precise and efficient response. This innovative approach allows us to leverage the vast knowledge encapsulated in academic papers, making our tool more robust and versatile. In the figure, you can see a visual representation of our paper-based retrieval-augmented tool usage, which further illustrates this process. On this slide, we delve into the technical details of our research. The figure you see here illustrates our paper-based retrieval-augmented tool usage. This approach is designed to enhance the accuracy of tool usage, particularly in complex scenarios. We conducted an ablation study to dissect the impact of each component of the academic paper on instructing tool usage. This study revealed that incorporating the paper content, particularly the abstract and introduction, significantly improves the accuracy of tool usage. Interestingly, adding more paper components did not lead to further improvement, indicating that the abstract and introduction often cover the tool function and potential applications comprehensively. Furthermore, we evaluated tool use accuracy within multi-turn conversations. This is crucial as in real-world scenarios, models need to correctly use the tool based on the context within a multi-turn dialogue. Our model, ChatHuman, demonstrated superior performance in this setting, showing its capacity to understand the comprehensive context information within the multi-turn dialogue and correctly use the tool to solve the problems. In summary, our research proposes a novel approach to improve tool usage accuracy, and our experiments validate its effectiveness. On this slide, we delve into the technical details of our proposed research. As you can see in the figure, we've introduced a novel method for tool usage, which we call the paper-based retrieval-augmented tool usage. This method is unique in its approach and has shown promising results. The core of this method lies in merging the retrieved sample with the user query. This combination is then provided to the agent as an in-context-learning example. This approach is a departure from previous methods and has shown to yield improved results. In essence, our method is designed to enhance the accuracy and efficiency of tool usage, making it a significant contribution to the field. We believe that this approach will pave the way for more advanced and efficient tool usage in the future. On this slide, we delve into the technical details of our proposed research. As you can see in the figure, we've developed a paper-based retrieval-augmented tool usage mechanism. This approach has led to significant improvements in the accuracy of tool usage. But how did we achieve this? We found that incorporating the content of academic papers into the process was key. In fact, the abstract and introduction sections of these papers were particularly effective. These sections often provide a comprehensive overview of the tool's function and potential applications, which proved invaluable in our work. This approach has not only improved the accuracy of tool usage, but also demonstrated the potential of academic papers as a rich source of information for tool instruction. This is a promising direction for future research and development in the field. On this slide, we delve into the technical results of our research. We found that the choice of the language model for value extraction doesn't significantly impact the results. This means that our method is flexible and can work with different models, enhancing its adaptability. Moreover, the performance of our method remains robust, regardless of the text embedding model used. This demonstrates the resilience of our approach, making it a reliable solution in various scenarios. In the figure, you can see a visual representation of our paper-based retrieval-augmented tool usage. This innovative approach has been instrumental in improving the accuracy of tool usage, making it a significant contribution to our research. In essence, our method is not only effective but also versatile and robust, capable of delivering consistent results across different models and scenarios. Let's delve into the technical results of our study. As you can see in the figure, we've developed a paper-based retrieval-augmented generation, or RAG, mechanism. This innovative approach uses academic papers to improve the accuracy of tool usage. Interestingly, we found that the abstract and introduction sections of these papers were the most effective in guiding tool usage. This is likely because they provide a comprehensive overview of the tool's function and potential applications. We also discovered that the choice of language learning model for value extraction didn't significantly impact the results. This is a testament to the robustness of our method, which remained consistent regardless of the text embedding model used in the retrieval process. Finally, our system, ChatHuman, excelled in multi-turn dialogue settings. This demonstrates its ability to understand complex context information and use the appropriate tool to solve problems. This is a significant step forward in our field, and we're excited to see where it leads. Begin a frame title, conclusions and remarks. Begin itemize, item further insights and findings. Begin itemize, item the paper-based RAG mechanism significantly improved tool usage accuracy, as demonstrated in our ablation studies. Item incorporating the abstract and introduction of academic papers into the prompt achieved the best performance, indicating these sections often cover the tool function and potential applications. Item the choice of the language learning model for value extraction did not introduce a significant difference, suggesting the robustness of our approach. Item our method, ChatHuman, demonstrated superior performance in multi-turn dialogues, showing its ability to understand comprehensive context information and correctly use the tool to solve problems. End itemize, end a frame.